Assalamu alaikum. I welcome you all to another lecture of EE434. Previously, we have discussed the non-isolated topologies of a DC to DC converters that were all operating in a continuous conduction mode. But what happens if we have a light loading condition such that the inductor current becomes discontinuous? To analyze the operation of a converter in a discontinuous conduction mode, in this particular lecture, we shall be having some analysis of the converter that operates in a discontinuous conduction mode. And in this lecture, we shall discuss the buck converter operation in DCM and as well as the boost converter operation in the discontinuous conduction mode. So let us start with the today's lecture. Discontinuous conduction mode refers to a situation where the inductor current becomes zero. So let me draw one converter which is a buck converter. So we have this IL, this is plus minus VL T, and we have this I naught, this is plus minus V naught, C, this is D, this is Q, and this is Vs. Now if we have a variable load such that we increase this resistance so that the current requirement of this load decreases, then there comes a point when the I, which is the current flowing here, which is this current I, it becomes less than the delta IL, right? Under these circumstances, the inductor current becomes discontinuous and hence the system is said to be operating in a discontinuous conduction mode. So we will first of all draw the key waveforms here and then we will analyze the transfer function based on the discontinuous conduction operation, discontinuous operation of this buck converter. So in a discontinuous conduction mode, we have these are the three subintervals. The first subinterval is when we have this Q on such that we have the inductance connected with this capacitor and we have this load resistance here. So this is IL, this is plus minus VL, this is plus minus V naught. During this particular time, if I apply the Kirchhoff's voltage law in this closed path, then by using the KVL, we have, this is Vs, we have minus Vs plus Vl plus V naught, that is equal to 0. So this Vl is equal to Vs minus V naught, and that is equal to L dIL over dt, and this dIL dt during this subinterval is equal to Vs minus V naught over L, which is the same as that of the CCM mode. There is another sub circuit that happens when we turn off the switch Q. So if this switch Q is now turned off, this diode becomes turned on and hence we have the current through the inductor that is based on, this is the IL, we have this plus minus VLT, we have this plus minus V naught, and in this particular circuit, if I apply the Kirchhoff's voltage law in this particular loop, then by applying the KVL here, we have VL equals to minus V naught. In the DCM operating condition, discontinuous conduction mode, the third interval is the interval when the inductor current becomes equal to 0. When the inductor current becomes equal to 0, we have another circuit available where this inductor is now in open circuit. Neither this diode is conducting nor we have this switch Q connected with this Vs. So therefore, this is the circuit during the subinterval T. this VL becomes equal to 0, right? So if we draw the waveform of the inductor voltage during these three subintervals, then we have, this is VLT. During the first subinterval, this is Vs minus V naught. During the second subinterval, we have equal to V naught, and during the third subinterval, we do not have any voltage across the inductor because there is no current that flows through the inductor. So consequently there is no voltage. So let me say that this is D1 Ts, this duration is D2 Ts, and this particular duration is D3 Ts. Also, if we draw the waveform of the current that flows through the inductor during the time D1 Ts, because it's a discontinuous conduction mode, therefore it will start from 0 point and it will reach to some maximum value, and thereafter it will come back to this 0. It will remain 0 until we have the new switching cycle available, and this particular slope is again, it is Vs minus V naught over L. This particular slope is minus V naught over L, and the same thing is happening for D1 Ts time duration and D2 Ts time duration. We do not have any current flow, and therefore this is D3 Ts, as obvious from the voltage waveform as well. So let us have the transfer function using the volt second balance of the across the inductor. So if I apply the volt second balance, if I apply the volt second balance here, we have Vs minus V naught into D1 Ts plus D2 Ts times minus V naught is equal to 0, because this is already 0, so we don't need to cater for this D3 Ts. This Ts is gone, so we are left with Vs D1 minus V naught D1 minus V naught D2, that is equal to 0, and using this we have this V naught equal to Vs into D1 divided by D1 plus D2, right? So this is the transfer function of the buck converter operating in a discontinuous conduction mode. Here we have a very important point, that the value of this D2, it is unknown. We never know at what value of D2 the current becomes equal to 0. So we need to establish some expression so that we would be able to express the transfer function of this particular converter or the voltage gain of this particular converter only using the D1 or using the values of the component that are known to us. To do that, the strategy is a little bit different for this buck converter. The first thing here is that we know that by using this ILT, which is the current flowing through the inductor, and because this inductor is connected across the output side for D1 and D2 both of the time, therefore the average value of through this inductor current is of very much importance. Now if you see here, we have earlier discussed that the average current or the DC current flows through the load. So whatever is the IL average, it flows through the DC current, and it constitutes this I naught, which is equal to V naught over R. So using this particular expression, we have this one is the maximum current I max, and here we have somewhere we have the IL, and this particular point, from this particular point to this particular point, we have delta IL. Now what is the average value of this IL using this particular waveform? Of course, it is IL average value is the average value is half the area under this particular triangle. So what is the area under this particular triangle? If you see here, this is D1, this is D2, of course TS with D1 TS and D2 TS. So the average value IL, this IL average value is equal to half the area under this particular triangle. So this IL is equal to half into D1 plus D2 into the height, which is the I maximum, because I maximum is the height of this particular triangle. Now let us say this is our equation number A. Now using the using this particular equation, which is waveform, which is the Vs minus V naught, we know that now using the voltage waveform, we know that the VL is equal to L dIL over dt. So during the time when the switch is turned on, we have dIL over dt equals to Vs minus V naught over L, and that is equal to, and that dIL over dt, or the slope of the current, is equal to delta IL over delta t. This delta IL over delta t, which is nothing but d1t, because during this time d1ts, the current rises from this 0 point till the maximum point I maximum, and therefore the net change or delta IL is equal to I maximum. This delta IL is equal to I maximum minus I minimum. Since I maximum is there, I minimum is 0, so therefore this equation can be written as dIL over dt is equal to I max divided by d1 into t, right? And I will write it here as delta IL is equal to I maximum minus the I minimum. And since this I minimum is equal to 0 for this DCM mod, so this delta IL becomes equal to I maximum, and therefore it is substituted in this equation in place of this delta IL. So dIL over dt is equal to I maximum into d1 of t. Now here from this particular equation, this I maximum is equal to delta IL is equal to Vs minus V naught over L into d1t, and this particular point Vs minus V naught over L d1t, this is equal to V naught into d2t divided by this inductance L, right? So we can have the maximum value either from the on time or from the off time. So if I put this value in the equation number A, which is here, if I plug in the value of this I maximum here, then we can actually find out the expression. So putting the I max equation in A, then we have half of I max into d1 plus d2 is equal to half into V naught d2t over L into d1 plus d2, that is equal to V naught over R, right? Because this half of I max into d1 plus d2 is the average value which flows through the load resistance R. Now from this particular point, from this particular equation, it comes out to be equal to d2 square plus d1 d2 minus 2L over RT, that is equal to 0. Now using this equation, particular equation, and by using the concept of the quadratic equation, this particular system can be attributed using the quadratic equation, that says that we can find out the value of d2 is equal to minus a minus d1 minus b plus d1 square plus 8lrt divided by 2, and therefore this v naught is equal to vs into d1 plus d2, that is equal to vs into 2d1 divided by d1 plus d1 square plus 8l over RT, and this gives us the value of the transfer function for a buck converter which operates in a discontinuous conduction mode. Important point here is that the boundary condition between the CCM and the DCM occurs when we have D2 equals to 1 minus D1, right? So on the similar grounds, we shall now try to solve for the DC to DC boost converter, and thereafter we will move on to the next type of a converter. let us move on for DCM for a boost converter. Now for a boost converter, let me first of all draw the waveform, draw the circuit here. This is the circuit. So we have this diode here, we have a capacitor here, and this is the resistance here. Now the key waveforms for this boost converter, the first one is the current through the inductor, that shall have this type of a curve. So this is I max, right, and this is the delta IL. This is D1 time Ts, and this is D2 Ts, and this is D3 Ts, and combined we have this whole switching cycle. This is ILT. The second important point here is that we have this type of a voltage across the inductor. So this is Vs minus, this is equal to Vs when we have a switch connected to position, when the switch is on or when the Q is on, this is equal to Vs, and here we have Vs minus V naught, and thereafter we have this 0. This is D2 Ts, this is D1 Ts. Another important point here is that the load current is now, we can find out the load current by averaging the current that passes through this particular diode. So during this particular time when we have this switch Q, during the time D2 Ts, the switch Q2 is closed, and therefore during the time when the switch is closed, then D2 conducts, and therefore this is the current, of the through the diode, which occurs with, in the time instant D2T. So this is ID as well. So first of all, by using this volt second balance, we have using the volt second balance across the, using the volt second balance on the inductor. So we have Vs into D1 Ts plus Vs minus V naught into D2 Ts, that is equal to 0, and this gives me V naught is equal to Vs into D1 plus D2 divided by D2. So let us say this is equation number A. This is equation number A. Now the next thing is we need to average this ID, just like we average the inductor current in for the buck converter. Here we have the diode connected on the output side, and therefore we will be using this to identify what is the current flowing through the load. So the average ID is equal to half, because this point is, again, this is I max. So by using the area under the triangle, half I max, so that is equal to D2T, and the height is this I maximum. So we get half I max into D2, and of course this whole is, since it is average over 1 over T, so this T will be cancelled out. So let me say this is my equation number 1. Now this I max is equal to delta IL, and that is equal to Vs D1T divided by L, because this is the net change in the current through an inductor can be attributed using the off time or the on time. So if we say that this ID is equal to half I maximum into D2, then this I maximum is actually the delta IL, which is the net change in the inductor current, and that can be attributed either by the on time or for the off time. So if we see for this current waveform here, we have this is equal to Vs over L, and if I multiply it with this D1 Ts, I will get the value of the maximum current I max. So here we have I max equals to delta IL is equal to Vs D1T over L. So this is my equation number 2. Now if I substitute this equation number 2 back in here to as a value of this I max, then this IT is equal to 1 over 2 into Vs D1T L into D2, right, and that is equal to V naught over R, because the average value of the diode current is can only flow through the resistance R. Average value of the current ID cannot flow through the capacitor, because capacitor will offer infinite resistance to a DC value, and therefore the average value of this inductor of this diode current ID shall only flow through the load, which is given as this V naught over R. So this D2 is equal to V naught into Vs into 2L divided by R d1t. And if I substitute this, let us say this is 3, so using the 3 in equation number A, which is here, which is this particular equation, if I plug it in here, then we can find out the value of the capacitor as V naught over V s square minus V naught over V s minus d square RT over 2L, that is equal to 0. And using the solving for this V naught over Vs, that is equal to half into 1 plus under root 1 plus 2 d square RT over L. And the boundary again for this as well, the boundary between the CCM and the DCM mod comes when we have this d2 equals to 1 minus d1. So this is how we have seen that the discontinuous conduction mod adds complexity in the analysis of the DC to DC converters. The design is usually based on a DCM for most of the reasons that we do not have knowledge about the load. However, if the load is specified, CCM mod is considered more feasible and easier to design compared to the DCM mod.